Alright, so today we're going to talk about matchings in a bipartite graph. So what is matching? Matching of a graph is a set of non-loop edges pairwise not adjacent, right? So in which no two of them share an end, right? So matching is just a set of edges that looks like this, right? And we don't want to have a loop in the matching. So this is matching. This is not a matching. All right. Now, what we are interested is the size of maximum matching. So let's write a function. So nu of g is the size of a maximum matching. So for instance, and so far all these definitions are for general graphs. So for instance, if this graph, if g is k1 and u of k1 is 0, it's not 1, it's 0. If it's k2, then u of k2 is 1 because I can take this single edge, and u of k3 is 1, right? Because I can take one edge, and u of k4 is 2 because I can take these two edges, right? So the size of maximum matching is nu. And one way to get a lower bound, lower bound? Yeah. Yeah, one way to get an upper bound of nu is the following. So we take tau of g. So here we have a minimum. Now we have a, nu of g is the size of maximum matching. Now tau of g is going to be minimum size of a vertex set meeting every edge. Every non-loop edge. Well, why not? So now I'm debating whether I should say non-loop or not. Yeah, let's not say that. Okay, doesn't matter. So for instance, so this is what? This is size of set hitting every edge. So for instance, if I have a k3, then tau of k3 is 2 because I need cover at least 2 vertices so that every edge has at least one end in one of these red sets. I cannot cover all 3 edges by one vertex because then there will be an edge left over. How about C4? Well, here I can cover by this diagonal vertices, right? So those 2 vertices will cover every edge. So that's 2. What about C5? The best thing I can do is each vertex can cover 2, so I need to cover 3. How about C6? Now I need to cover these 3. right? Now let's compare these numbers with nu. So nu of K3 is 1. That's the size of maximum matching. How about, oops, yeah, how about nu of C4? Well, that's 2 because I can cover these two. And nu of C5 is again 2 because that's the best possible. And nu of C6 is 3. Right. Now, if you look at these two numbers, these are different. And they are same. But one thing is clear. If you look at the definitions, if you compare nu and tau in any graph, tau has to be at least nu. Why? Because if I have a matching of size k, then no matter how you have a set of vertices meeting every edge, you're gonna have to cover at least one vertex from every edge in the matching. So that means tau is going to be at least the size of matching. So tau gives you a natural upper bound on the size of matching in a graph G. But in general, the equality does not hold, right? We are seeing this count example over here. Equality doesn't hold. Here's another example where the equality fails, right? Now, here's a theorem of Koenig in 1931 saying that if graph is bipartite, then nu of G is equal to tau of G. So surprisingly, as long as the graph is bipartite, this natural upper bound gives exact number. Okay, and Koenig is the first one who wrote the textbook on graph theory in German in 1930s. So we're gonna prove this. So how are we gonna prove that? So we're gonna use the idea of alternating paths and augmenting paths. Okay, so a path P is M alternating with respect to M if, okay, so let me write P as V0, E1, V1, E2, V2, EK, VK. So path is M alternating if every other edge, all these even edges, I mean the edges in the even locations, so E6, these are in M. Then we say it's M alternating. Okay. Now, path P is M augmenting. Oh, I should say, I don't have to say with respect to M. Or what I mean is, or alternating with respect to M. So M augmenting or augmenting with respect to M if it is M alternating and V0, Vk are not incident with edges in M. So the first vertex is not incident with an edge in M, and the last vertex is not incident with an edge in M. Then we say it is an M augmenting. Now, here's a nice observation. A matching M is maximum if and only if graph G has no M augmenting path. Okay, so the existence of, so if I want to say that some matching is maximum, one way to say that is there is no augmenting path. If I want to say that some matching is not maximum, of course I can find the bigger matching, but another way of saying that is find the augmenting path. So why is this the case? It's not terribly difficult. So for instance, let's prove this direction. Suppose G has an M augmenting path P. So what does that mean? I had a path, no, this is M, and we had a path that is augmenting, right? So this is a P. Now let M prime be the M delta, the edges of P. So delta means the symmetric difference. It's x minus y union y minus x, right? So instead with these red color edges, what we end up is, by symmetric difference, the intersection will be removed. So those three edges are removed from M. Now it's added into M prime. No, they are removed from M prime, and these edges added. So what you end up is, so those blue edges are M prime, right? Now it's easy to see that size of M prime is size of M plus 1, and M prime is a matching. So it's contradiction to the assumption that the M is a maximum matching. All right. How about the converse? Right. Suppose graph has no augmenting path. How do we know that it is a maximum? So suppose M is not a maximum. Matching. So that means there is a matching and N such that size of N is bigger than size of M, right? Because it's not a maximum matching. So when we say something is maximum, it's about the number of edges. So there will be a bigger matching whose number of edges is bigger than size of M. Now, what we are going to do is look at the symmetric difference between M and N. So let's consider M delta N. Now, this is set of edges, right? So, okay, let's say H be a subgraph of G consisting of edges in M delta N. Now, each vertex is instant with at most 2 edges because this is a symmetric difference. So that means each vertex has at most 2, so degree at most 2. And H is also simple. Right? No loops, no parallel. I mean, it may, H may have a parallel edges, so let's not say simple, but H has no loops. What does that mean? So if you have a graph whose maximum degree is at most 2, then it's easy to see that the graph, every component of that graph is either a path or a cycle. Right? So these are the only possible things. Now, if you have a cycle, what does that mean? Every vertex has even degree, so you have one edge from M, the other edge from N, and one edge from M, the other edge from N. That's the only way you can create a cycle in this symmetric difference. Because every vertex has degree 2 in the cycle, so that means you're not going to delete any edge, right? Each vertex in this cycle must be instant with one edge in M, one edge in N. So this is M, this is N. And so that means every component isomorphic to a cycle has an so let me say in every component the number of edges in M is equal to the number of edges in N, right? Because it has to alternate. It's matching, so no 2 edges from M will have a common end. But we remember the number of edges in N is bigger than M. So cycles are not a main problem for that, right? So that means, cycles always have a balanced number, right? You have a same number of edges in M and N. So that means there is a path. There is a component that is a path in H, path P in H such that number of edges of M, when you compare number of edges in M, then you have more edges in N. So how is it possible? Again, all the edges in the middle, all the vertices in the middle are instant with M and N at the same time. So the only possible way is to alternate. Right, so this is the only possible way, and that means P is M augmenting. That's contradiction. That's contradiction because we assume the graph has no augmenting paths. Okay? Now, this is kind of a certificate which says that something is a maximum matching or not. And we're going to use this to prove the Kleenex theorem. Right? So remember, Kleenex theorem says that nu is equal to tau whenever graph is bipartite. But trivially, one direction is easy, right? So we already have seen that. So it's enough to show that nu is at least tau of g, right? So to show that, I will take a maximum matching and then see if I can find the set of vertices covering every edge. Okay. Now let M be a maximum matching of G. So you have a maximum matching and graph is bipartite. So let A be a bipartition of G. Graph is bipartite, so you have two parts. Okay, let me draw a bigger picture. So this side is A, this side is B. All right. Now, what we're gonna do is to use the fact that graph has no M augmenting paths. Okay. So let's say X be the set of vertices in A intersection V of M. So let me write just this notation, V of M, that just represents the set of ends of edges in M, but it's intersection with A. So this is a set X. Right? Oh no. Okay. Let me fix. Set of vertices in A intersection V of M. Now I want to add the extra condition that has an M alternating path to B minus V of M. So I'm interested in these vertices, and some vertex has an alternating path. So for instance, maybe it might go directly. So this is in X, right? So that's the alternating path of length 1. Or you can start from here and go there and turn left and go there. Oh, no. Not there, not this way. You start from here. You first use edges not in the matching, and then you use edge in the matching, then you go to the B minus X. B minus V of M. So that's an alternating path of length 3. So that's also in X. So you might have something like this, and all these vertices are in X. Okay? So these are the vertices having alternating paths from that ends in B minus V of M. All right. Now, what are we going to do? Now, let Y be the set of vertices in B intersection VM that are not matched to a vertex in X by M. So matching edges M will pair a vertex in X, a vertex in A and vertex in B. So the vertices that are left over, so the partners of X will not be in Y, right? So those vertices, among those vertices in V of M intersection B, I'm going to choose the vertices whose pair is not in X. So that's going to be Y. All right, so what's the claim? I claim that X union Y meets every edge. Of G. So why is this the case? Let me argue a little bit. So we are covering this set together with that set, right? Are there any edges left over? Well, if I have an edge, so let's look at from the A side. Edges instant with X, we don't care already, they are covered by X. Edges in A, can I have an edge like this? No, because if I do have an edge like this, then I'm going to have a bigger maximum matching. This is augmenting path, by the way, right? Augmenting path of length 1. How about edges from here to there? Well, it is possible, but if I have such an edge, then I'm gonna have an augmenting path. Oops, so that means so I'm gonna have augmenting path starting from here, follow the matching edge, and then I go to B minus V of M. So this is augmenting path. If I go here, I go like this, that's augmenting path, but graph has no augmenting path. So that's not possible. So I don't have edges from A minus V of M to the Vm minus Y. So there's no edge from here to the right hand side, unless you can have an edges like this. But you cannot have edges from here or edges from there. How about, and then okay, how about, how about these people? Well, if I have an edge like this, then I'm gonna have an augmenting path, an alternating path, which means that I have to put this vertex in X, which is not the case. So I don't have edges like this. How about this? Again, the same region. If I have an edge like this, I will have to put this vertex in X. These are not vertices not in X, so they are not. There's no edge like this. Okay, so every edge from these vertices will be instant with Y. How about from the other side? You don't have edges like this, you don't have edges. Oh yeah, we already did argue everything, right? So there's no edge like this, no edge like this, no edge like this, no edge like this. So that means every edge will be instant with X or Y. So therefore, tau of G is the minimum size of set of vertices meeting every edge. So this will be less than or equal to X union Y. This is same as the size of matching, which is equal to nu of G. Right? So that's the proof. Okay, and if you think of so this is a perfectly fine proof for me, but you can think of it as an algorithm. So if you're given a graph G, bipartite graph G, this algorithm will algorithm starts with the matching, which is empty set, and then you keep finding augmenting paths. So as soon as you find augmenting paths, you can increase the size of your matching by 1, right? By augmenting. And then it will increase the size of your current matching by 1. Then you keep doing that. Eventually, so you do it at most like n over 2 times, right? Because that's the maximum of the matching. And you do it at some point, you're going to be stuck, right? You will not be able to find the augmenting paths. At that time, you know that this is a maximum matching. And not only that's a maximum matching, you can also find this set of pairs, no, set of vertices hitting every edge. So you can give two things. One is maximum matching in a bipartite graph, and the other is the certificate why this is maximum by showing that you have a set of vertices hitting every edge. Right. So this is kind of an algorithm. All right. Now, as a corollary of Kleenex theorem, we can prove so-called the Holtz theorem. So let me state the Holtz theorem. But this is actually quite well known. So Holtz is a British mathematician. So Holtz theorem concerns about the case when you have a matching covering one side. So let G be a bipartite graph with a bipartition AB. Then G has a matching covering A if and only if. So graph has a matching covering A if and only if neighborhood of S is at least S for all. Yeah, so what is that? So you have AB. Now you think of the, so we are trying to find the maximum. No, you're not trying to find the maximum match. I'm trying to find the matching covering every vertex in A. So what is the natural condition that prevents me having such a matching? Well, one situation is maybe you have only 3 people in A and 2 people in B. That's one case, right? So no matter how you try to have a matching, where size of maximum matching is at most the size of B, so like one vertex will be left over. So that's one condition. So this is the case when size of neighbors of A is smaller than size of A. How about, but that's not the only obstructions. It may be possible that if I look at the subset S of A, well, the number of neighbors is so small so that when you look at when you compare this thing, maybe neighbors is too small, so that this is kind of certificate why you cannot have any matching covering A. So this is natural condition, right? Now, oh, remember what is this notation? So this N of S is set of neighbors or vertices in S not in S. Right? So in other words, N of S is union of N of V in S minus S. So Holtz theorem says that whenever you have a matching covering A in a bipartite graph, then this easy condition is satisfied, but that's easy direction. But the more important direction is the converse. Whenever you have this inequality satisfied, then you're gonna have a matching covering A. And I will show you several proofs because each proof gives us some idea. So the proof 1, let's use Kleenex theorem because we just proved it, right? So this direction is easy. We only care about the converse, right? So suppose that for every subset, the number of neighbors is bigger than the size of S. Now, I want to prove that there is a matching covering A. How do we prove that? Right. So if X is a set of vertices, meeting every edge, right? If you have an X meeting every edge, then what can I say? So this is A, this is B. That means there's no edge from so A minus X to B minus X. Right? So that means neighbor of A minus X is subset of B intersection X. Right? All the edges over there. Now, what does that mean? That means neighborhood of A minus X. I know that B intersection X will have more vertices, and size of B intersection X is at least size of neighborhood of A minus X, but by the assumption, this is at least A minus X. Right? Yes. So B intersection, so A minus X plus X is an, oops, let me say this. A intersection is like B intersection plus A intersection X. So this is equal to X, and that's equal to A. So we prove that size of X is at least the size of A. So tau of G is at least size of A. And by Kleenex theorem, this means that nu of G is at least size of A. Right? But if graph has but the maximum size of nu cannot be bigger than, strictly bigger than size of A, because that's size of one side. So that means nu is going to be equal to A, and you have a matching covering A. So that's the first proof by using Kleenex theorem. Okay. Now I'm going to show you direct proof by using induction. There are many proofs of Horst theorem. So this is second proof. So I'm going to use induction on, this time induction on, let's say, A. Alright. So what does that mean? That means I'm going to think of the count example with the minimum size of A. Right? So if size of A is really small, if A is less than or equal to 1, then it's trivial. You can just check. Right. If A is empty, then trivially there's a matching covering empty set. If A has size 1, the neighbor of the single vertex is size at least 1, so you have an edge. So I can assume the size of A is bigger than 1. Now I will split the case into two cases. Case 1, neighborhood of S. Okay, so do I wanna use S? Okay, neighbor of X is bigger than X for all X, which is non-empty and proper subset. So this first case is when you don't have any equality in the middle, right? So this is whenever you take a subset X, you have more neighbors. So you have redundancy. All right. In that case, let's pick a. Yeah, let us pick an edge E, which is AB in. So A is a vertex in A, and B is a vertex in B. So I'm gonna choose arbitrary edge AB. All right. Now let's consider a new graph G prime, which is G minus A minus B. So we're gonna delete these two vertices from graph. So that's gonna be my G prime. Now in G prime, when I look at the neighbors, right, in G prime, for all S, which is A minus A, neighborhood, okay, neighbors of S in G prime is actually an, okay, let's ignore empty set. So it's gonna be neighbors of G. I mean, I have one redundancy, right? Because there's a possibility that this vertex, oops, there's a possibility that neighborhood of S may contain A, so I have to remove one. But still, by the assumption that equality never holds, so this is at least S. So therefore, G prime has a matching M prime covering A minus A. Now let's take M to be M prime union E, right? So that's this edge AB, right? Then M is a matching covering matching of G covering A. So that's a easy case. So when you have no equality for all non-empty proper subsets of A, then I can choose one edge as I like. I still have a redundancy, so even if I lose one, I still satisfy Horst inequality. So therefore I can find the matching. So how about case 2? Case 2 is the other case. If nx is equal to x for some x which is non-empty, which is n proper subset, then, right, so here's a, here's a b, here's x, and neighborhood of x has the same size. Now we're going to apply induction over two things. So this is one, and over here as well. Okay, so let's say this is G1. So let G1 be the graph induced on X union neighbors of X. Okay, G1. And G2 be graph G delete X, delete N of X. So by the induction hypothesis, G1 has a matching M1 covering X. Why? Why can I apply induction? The thing is that A intersection X is strictly smaller than, no, actually I don't have the intersection. The thing is, size of X is strictly smaller than A, so we can apply the induction hypothesis. Remember, the induction was the size based on the, so the induction parameter was size of A. Okay, so and what is the other reason? N of S is size of S. NG1. Why is the second whole? Because whenever you look at the subset of X, this is S, right? There's no neighbors here, right? All the neighbors of S are here. So N of G1S is equal to N of GS. And we knew that N of GS is at least the size of S, right? So this is N of GS, and that's at least the size of S. So the Hol's inequality holds. So therefore, by induction, G1 has a matching covering X. How about G2? Now, I claim that for S, which is subset of A minus X, neighbor of S is at least size of S. Why is this the case? So here's X, here's a neighbor. You may wonder, you may worry that S may have neighbors in both top and bottom. In that case, neighbor of S may contain people here and people there. And so you may end up having more vertices than you can afford, right? So how do we prove this? The way we prove that is use this observation. So NG2, okay, let me say it this way. NG of S union X. What is the neighbors of union of X and S? That's gonna be neighbor of X union and G2S, right? Now what we carry is neighbor of everything together with S. Now that means NG of S union X is equal to NG of X plus NG2 of S. And I know that this is equal to size of X, and this is what we are looking for, right? And by the assumption, this is less than equal to S union X, right? Oh, not less than equal to, greater than or equal to. This was a given. So therefore, NG2S is greater than or equal to S. Thus, again by induction hypothesis, we are using the fact that X is non-empty. Since X is non-empty, G2 has a matching M2 covering A intersection G2. Then M1 union M2 is a matching covering A. Okay, so that's the second proof. All right. There's another proof based on induction on number of edges. But I'm going to skip that. You can try to delete an edge, E, right? So this is what you can do, right? If I delete an edge and I still satisfy Hall's inequality, then I win, because I can find the matching not using this edge E. So that means whenever I delete an edge, there is a place where the inequality fails, and you can use that to prove that the graph is of a particular type, and there you can easily deduce that, easily prove the theorem. But anyway, you can try. All right, so now let me briefly cover a few corollaries. So here's a one corollary. Let K be at least 1. Now, graph is K regular if every vertex has degree K. I want to prove that every K regular bipartite graph has a perfect matching. So what is perfect? A matching is perfect if it covers every vertex. Then it's a perfect matching. So if a bipartite graph has same degree at every vertex, then it has a perfect matching. Why is this the case? So first of all, it's easy to see that size of A is equal to size of B, because number of edges in G is equal to K times A, which is equal to K times B, right? Because every edge is in the middle, and each vertex on the left hand side is instant with exactly K edges. Each vertex on the right hand side is instant with exactly K edges. So if you take total number of edges, then you can count in two different ways. If you count with respect to A, then you have a K times A. You count with respect to B, you have a K times B. Now, if hypersets S, then number of edges incident with S is exactly K times S, right? But if you look at the neighbors, every vertex has at most S edges in, at most K edges incoming, but some of them will have some edges coming out of S. So you can easily see that every vertex, so the number of edges instant with the S will be at most K times n of S. So that means n of S is at least S, right? So therefore, G has a matching covering A by Hall's theorem. So that means G has a perfect matching, because size of A is equal to size of B. So if you have a matching covering A, then you have a matching covering B as well. The same matching covers B as well. All right, so that's the nice easy corollary. And here's another corollary due to Peterson in 1891. Okay, so now let K be even. Then every K regular graph has a 2 factor. What is 2 factor? It's a 2 regular spanning subgraph. Right, so one vector, okay, let's say k vector, is a k regular spanning subgraph. So in particular, one vector is a subgraph whose edge set is a perfect matching. Right? Every vertex is instant with exactly one edge. One non-loop edge. I don't care about loops. So in this corollary, the theorem of Peterson in 1891, we showed, it says that if graph is regular and every vertex has even degree, then you must have a two vector. And we can prove it by using this above corollary. So why is this the case? Here's an interesting, brilliant idea. So if I have a graph G, I will construct a bipartite graph. How do I construct? You make copies of the same vertex set twice. Right, so each vertex is copied into two vertices, and whenever you have an edge, then I will copy it into two edges. Right? So G prime is a bipartite graph on. So if I write it, then this is more weird. So 0, it's cross product, right? So the V of G times 0, 1, such that X, let me say this way, Xi is adjacent to Yj in G prime if and only if X is adjacent Y and I is different from J. Oh, but no, that's not a good idea. Let me go back a little bit. Now, I want to construct bipartite graph, but I want to have a clever way. What's the clever way? There could have been one way to construct a bipartite graph, but now I'm using the fact that every vertex has even degree. Since k is even, G has an Eulerian circuit. Now, this sounds almost correct, but not exactly correct. So let me add one more condition. We may assume number of edges, k is even, so okay, we may assume that G is connected. Why? Because if graph is not connected, then I can work on each component, right? If every component has perfect matching, two factor, then whole graph will have two factors, so nothing to worry. So we can assume the graph is connected, and k is non-zero, so you have a non-empty edge set, so graph must have an Eulerian circuit. So let's say C. Now the orient edges following C. So if C goes this way, then I orient this way. Now, how do I obtain the new graph? Right, so let me say this way. From 0 to 1, if X is adjacent to Y and X is oriented the edge xy is oriented towards y in C. The C is the Eulerian circuit. So I need to have an example which is actually even alright. Okay, is that it's not a regular graph, but at least it's Eulerian. Yes. So how do I do that? Well, I first find the Eulerian circuit. So 1, 2, 3, 4, 5, 6. Okay. Then I will follow the edges according to this orientation. So this is one edge, first edge, second edge, third edge, fourth edge, fifth edge, and sixth edge, right? But remember that C visits every vertex k times. So that means each vertex has k incoming edges and k outgoing edges. That means G prime is k regular. Right? So you have a k incoming edges and k outgoing edges. Then by the previous corollary, G prime has a perfect matching because graph is bipartite. Now, what happens if you have a perfect matching in G prime? Right? So you have a perfect matching. It could be like this if you have a loop. Right? So if G prime has a perfect matching, then in G you have a 2 factor, because just look at the corresponding set of edges. This is 2 factor. So we obtain a 2 factor of G. So that's the proof. Right? So that's it. So in the next lecture, we will start proving theorems on matchings, perfect matchings in a general graph. Okay, so perfect matchings in bipartite graphs are much easier because we have all this Kleenex theorem and Hall's theorem. But in a general graph, similar theorem doesn't hold, but we will have a different theorem. Okay, that's it.